In this video, I will talk about the time constant and what is the usefulness of this quantity. You have seen when you charge or discharge a capacitor, the expressions that we get for the current in the circuit or the charge on the capacitor, they include something e to the minus t over RC. Now, because we often see this product, RC, we do define it, this is the Greek letter taf. We define this time constant with the Greek letter taf to be RC, the product of the resistance and the capacitance that we have on the circuit. Now, I want to point out something. In the exponent here, the numerator has units of seconds. And I know that the exponent of my exponent here needs to be without units. This means that the units of RC should be seconds. And that's the reason why we call this constant a time constant, because it does have units of time, seconds. Now, what is the meaning of this? If you set your time t, your numerator, to be equal to RC, which is your time constant, then essentially you're gonna get e to the minus 1. And this is equal to 0.37, roughly. Now, this 0.37 means the following. If this exponential is in your expression for the current, then the time constant here, let me show you the equation. So if your equation is I naught times e to the minus t over RC, if you have e to the minus 1, then this will be simply 0.37 I naught. And what this means is that your current at that moment in time is equal to 37% of what you had at the beginning. So say if my time constant here is at this point on the time axis, then this means that the 0.37 I naught is somewhere here. Okay. Now, why is this important? Well, let's say then, okay, that will be one time constant, this will be two time constants, and this will be three time constants. You can tell that if you wait a few time constants, then the current has decreased significantly. So one thing that you can do with the time constant is you can use it to see how long you need to wait until the capacitor, for example, until the capacitor discharges. So if you give me a circuit with a resistance of 1 ohm and the capacitance of 1 farad, then the product would be 1 times 1, it will be, my time constant would be 1 second. Then I can tell you without doing absolutely any other calculation, since your time constant is 1 second, I can tell you if you wait for 5 seconds, you're gonna see very, very little current, if any current, flowing in your circuit. If you have a different circuit where the product here gives you 60 seconds, okay, if this product ends up being 60, then I would say, well, if for that circuit, I would probably wait around 300 seconds or maybe 200 seconds before the current becomes very, very small. So the usefulness of the time constant is that it gives you an idea how long you have to wait for this circuit in order to have the capacitor discharged or charged depending on what you're doing. Okay, it just gives you an idea for how long you have to wait. Now I showed you that it's a simple product R times C, but what happens if you have two resistors? So let's say I have something like this. This is R1, this is R2, here is my capacitor. Okay, so this is C, R1, R2, and this is your EMF. Well, try to think. I can, in order to find what is the RC, I'm gonna need to transform that circuit to essentially this one. Okay, this is C. Let's call this the R equivalent, and this will continue to be the EMF. I'm charging the capacitor here. Now, how can I find the R equivalent? Because R1 and R2 are in series, the R equivalent is simply the sum of the two. So, if you ask me to calculate the time constant for this circuit, I will first calculate the equivalent resistance and then use that to find the time constant. So, for this circuit, this would be the time constant.